This is, as Rasmus said, envelopes. So before I get into the details of what I want to talk about today, I think it might be useful to spend a little time going over the timeline of the thought processes that led to this particular point. So that's what I'm going to do first, and I'm going to do that by going through a number of papers, just very, very briefly. So the timeline really starts in 2010, when, along with Bing Li and Francesca Chiaramonte, I published a new paradigm for dimension reduction in regression problems. That paradigm is referred to loosely as envelopes. The original context was for the multivariate linear model, but now it's moved well beyond that into context that I never would have imagined at the outset. The idea for envelopes is to informally look at the data and to envelop the part of the data that contains the information on the question at hand, and simultaneously leave behind a part of the data that's really immaterial to the question at hand. But what distinguishes envelope models from other models, or from other ways of doing dimension reduction, is we want to do that with a level of clarity that has not been possible in the past. And that level of clarity enables us to address problems with highly collinear predictors, and that's what gives us a hook into partial least squares. In a couple of years after I published that paper, Inge Helland, who has written extensively on partial least squares, was visiting Minnesota, and we began talking about the possibility of connections between envelopes and partial least squares. It turns out that through our efforts, we were able to show that there's a very close connection between envelopes and partial least squares. And in fact, partial least squares is an envelope method. That gave us a lot of additional insights into partial least squares. It provided a connection between partial least squares and standard statistical models. And it really brought partial least squares into a framework that statisticians, with which statisticians are familiar. Now, what paper number 2 didn't do is address one of the main attractions of partial least squares as I understand it. And that attraction is that partial least squares is at least advertised as being serviceable in high dimensional regressions in which the sample size is typically a lot smaller than the number of predictors in regression problems. We did not address that issue in number 2. And so between references number 2 and number 3, I launched into an effort with Liliana Ferzani to investigate partial least squares predictions in high dimensional regressions using envelope foundations that we set in number 2. That turned out to be a very detailed study. It took a lot of effort to get to the answers, but the answers were worthwhile because they showed that there are regression contexts, in particular contexts that are common in chemometrics, in which partial least squares can be expected to do a really excellent job. So from there, we were invited to do a perspective paper for chemometrics, and we wrote that paper titled Envelopes, a New Chapter in Partial Least Squares. We kind of revisited what we'd done in the past, and we put forth the idea that the underpinnings of envelopes provided to partial least squares allows us to get a better look at partial least squares. It allows us to extend the methodology and to firm up the methodology as it exists. And paper number 5, which is the topic for today, is kind of a first step in that line of using envelopes to better understand and extend partial least squares regression and other methods for that matter. So what we're going to be doing today then is talking about partial least squares regression algorithms in the presence of nonlinearity, and we're going to be using envelopes to underpin that discussion. Now, envelopes are not going to play a major role. I'm not going to be reviewing envelopes, but as you go along, I hope you will see how they're entering into the discussion. So to continue with today then, the context for today, nonlinear regression, and we're going to be treating linear regression as a special case. So the general context is simply that we have a response, univariate, and we think of that response as its mean function, expectation of y, given the set of predictors at which it's measured, x, plus an error. And we have a sample of size n, so that model holds for I equal 1 to n. The predictors, p by 1 vector, often p can be in the hundreds, which is a lot bigger than the sample size. And therein lies part of the problem. The mean function we're going to be largely assuming is unknown. So we don't know the mean function, which is characteristic of nonlinear regression problems. On the other hand, when we talk about linear regression or simply using linear prediction rules, we'll be setting the mean function to be a linear function of x, where beta is a p by 1 vector that gives appropriate weights to the predictors for describing y. The general goals are to learn about the mean function if we don't know it, to estimate beta if we assume that it's linear, and in either case, to do predictions. So that's the context. And the question for us today is, how does partial least squares fit into this context, if at all? Well, the answer is going to be that partial least squares fits neatly into this context, in a manner that I'm going to be describing in a couple of minutes. So to do that, to see how partial least squares fits into that very broad context, we need to bring two ideas together. The first is how PLS algorithms work. So standard off-the-shelf algorithms like NIPALS and SIMPLS, they generate a P by Q weight matrix, W hat, that's used to reduce the predictors mapping X to W hat transpose X. Now there's a hat on W here just to remind us that W depends on the data, so it's a function of the data. Q is the number of components, and typically the algorithms give a W hat that has orthonormal columns, so W hat transpose W hat is the identity, and that's fine since only the subspace spanned by the columns of W hat matter. I could take a W hat from the algorithm, multiply it on the right by any non-singular matrix, and the predictions that come out of the algorithm are going to be unchanged. Now we have to take that aspect, which I'm assuming you're all familiar with that kind of property of PLS algorithms, and we're going to use that in conjunction with the central mean subspace. Now the central mean subspace is something that I proposed with Bing Li in 2002, and the idea is pretty simple. So let's think about a P by M matrix theta. M is going to be less than P, and hopefully M is a lot less than P. We want M to be as small as possible so that the mean function, the expectation of y given x, is exactly the same as the expectation of y given theta transpose x for all x. And what this means in a dimension reduction context is that we can take our P by 1 vector of predictors, and if we knew theta, we could discard it in favor of the M by 1 vector of linear combinations, theta transpose x. If M is small, that's a substantial reduction in dimension, and that greatly facilitates the regression problem and understanding what the mean function is. Again, only the subspace spanned by the columns of theta matters. That subspace is called the central mean subspace, and the last line on the slide kind of gives you a hint why it doesn't matter, or why only theta hat, the span matters. And that's because the expectation of y given theta transpose x is the same as the expectation of y given theta times A, quantity transpose x, for all non-singular matrices A. So it's really only the column space of theta that matters. Change the column, change theta by multiplying by A, doesn't change the column space, and hence it's only the span that matters. Now we want to marry those two ideas together. And that's where the key observation comes in. So the next slide is our key finding. What we found is that W hat consistently estimates an envelope matrix W so that the span of W envelops the central mean subspace. That is, the span of theta is contained in the span of W. So if you know W, you've captured theta, or in the context of the name, you've enveloped theta, or the span of theta. So we know that M is therefore going to be less than or equal to Q. Remember, Q is the number of components, and M is the minimal number of linear combinations that you need to describe the mean function. And what that tells us is that the expectation of y given x is the same as the expectation of y given theta transpose x is the same as the expectation of y given w transpose x. So that's how partial least squares, NIPALS and the SIMPLS algorithms fit into this context. They give you a reduction of x that does not affect the mean function. Now, if we look at that series of equations, the series of equations says that I could discard x in favor of theta transpose x. I would lose no information if I knew theta. I could compute theta transpose x. My predictions would be exactly the same if I used x or theta transpose x. It also says that I could discard x in favor of w transpose x. On the other hand, we know that the dimension of M is going to be at most the dimension of Q, or Q. So the question arises, why am I thinking about partial least squares at all? Why don't I focus on theta? Because it's going to give me fewer linear combinations of x that are needed. The number of linear combinations of x typically produced by partial least squares will be bigger than M, bigger than that needed for theta. So perhaps my message should be, you need to abandon partial least squares and go with methodology for the mean function that has been developed over the past couple of decades. Well, that's not going to be my message. And that's because partial least squares has another aspect to it. And it's an aspect that isn't shared by methodology for estimating theta. And it's the aspect that allows partial least squares to work when the predictors are collinear. And that aspect is what I'm describing below the equation. So what I'm going to do is I'm going to take W, then I'm going to complete the basis. I'm going to add W0 so that W concatenated with W0 is a P by P orthogonal matrix. Then, envelope methodology, including partial least squares methods, require the clarity that we seek. And we manifest that clarity by requiring that the covariance between W hat transpose X, the material part of X, and W0 transpose X, the immaterial part of X, is 0. So we don't want there to be any correlation between the part of X that we keep and the part of X that we discard. That's what makes partial least squares works. That's what sets envelopes apart from other dimension reduction methodology. And that's why I would not recommend that you pursue theta in chemometrics applications, because the methods for estimating theta work really well when the predictors are at most moderately correlated. They fall down rather rapidly when the predictors become highly correlated. And that's because it gets hard for that methodology to identify the material part of X from the immaterial part of X. On the other hand, that step for partial least squares is relatively easy, because embedded in the methodology is the requirement that the material part of X, the part that we're going to keep, has got to be uncorrelated with the part that we're going to, in effect, discard. Now, if X happens to be normally distributed, then that covariance condition is equivalent to saying that the material part of X and the immaterial part of X are independent, and that's an incredibly strong condition in methodology. It means that W0 transpose X is in fact totally immaterial. You could discard it without any loss at all. So that's how partial least squares works, and that's the reflection of envelope methodology as it comes through partial least squares. And it's the unique part of partial least squares that covariance condition being 0 is what sets partial least squares apart from any other methodology, dimension reduction methodology of which I'm aware, understanding that partial least squares is a member of the general envelope family. Now, what does this imply? This implies that we can use the reduced regression working model, and given on the bottom of the slide, to carry on with the analysis. So all we do is take the mean function, we substitute in our estimates, and then we can carry on with the analysis. That's pretty much how partial least squares algorithms work, except they assume that the mean function is linear. So before I continue with the nonlinear aspect of things, I want to revisit linear partial least squares briefly to kind of give you something to play off of. Now, again, linear partial least squares works the same way, except we assume that the mean function is linear, or you say, I'm only going to entertain linear prediction rules. So points 1 through 4 on this slide are just a way of representing what happens inside partial least squares algorithms. So we select a number of components, use the algorithm to generate W hat, a standard off-the-shelf algorithm, NIPALS, SIMPLS, some of the variations. Then we set the mean function. We say, hey, I'm going to assume a linear mean function. Then we fit that linear mean function using ordinary least squares when n is a lot bigger than bigger than the number of components, which it typically is. That gives us beta hat partial least squares as displayed on the screen. And then we iterate and we select Q using cross-validation. We estimate prediction error based on a holdout sample. There's nothing new here. This is just how partial least squares algorithms work. We know a lot about how these characteristics of these algorithms. So I want to review some of those briefly. So a lot is known about off-the-shelf linear partial least squares. The first 2 points on this slide are really the highlights of what matters. If the signal is sparse, for example, if you're doing a chemometrics problem and only a few wavelengths matter, if you have 300 or 400 wavelengths measured, but only 10-ish matter or in the teens, then it's a sparse problem. Partial least squares, the off-the-shelf algorithms that I'm talking about, are not going to work well in that kind of regression. In effect, partial least squares is unserviceable in high-dimensional regressions that are sparse. And the reason is, intuitively, that the more things you measure that don't provide signal, the harder it is to separate out those things that do provide signal. So if you have 300 wavelengths you've measured and only 10 of them matter, it's going to get hard to find those 10. If you increase the number you measure to 400, it's going to get even harder to find those 10. 500, harder still. So partial least squares does not really work well in sparse regressions. And that really came out of our 2019 paper and a preview of that in 2018. On the other hand, if the signal is abundant, if you have a lot of predictors that matter, not just a little handful, if you have 300 or 400 wavelengths and at least a couple of hundred of those matter, you're going to be in really good shape. Partial least squares is going to give you excellent predictions, even if the sample size is small. In fact, the convergence rate for such predictions is at the usual root n rate in the scenarios I've described. And that's the typical standard rate of convergence, for example, for a sample mean. Partial least squares will work really well when the signal is abundant. Now, we also know, it's clear in the literature, that standard off-the-shelf algorithms are unserviceable in nonlinear settings. This was first pointed out by Wald, I think, in 1989, and he also gave the first proposal for dealing with such situations. And there followed from 1989 a proliferation of methods that continues today. It's like people are still trying to sort out what to do in nonlinear problems with PLS-like reasoning. There's been a recent adaptation using neural networks, but none of the methods that I've seen in the literature make use of the relationship that the expectation of y given x is the same as the expectation of y given w transpose x. Remember, this w comes from off-the-shelf algorithms. So here is what I would propose as a PLS method for handling nonlinear regression. Step 1, generate a W hat via a standard off-the-shelf PLS algorithm. In other words, use standard algorithms for the dimension reduction phase of the problem. Then number 2, estimate a prediction rule based on a working model. Expectation of y given w hat transpose x. So those are just the components. And as long as q is pretty small relative to n, many statistical methods are available. You're now in a problem that's been studied extensively in the statistical literature. There are smoothing methods and kernel methods, non-parametric methods and semi-parametric, just tons of methods that are available for handling these problems, provided q is small relative to n, which it typically is. It's really kind of hard to sort out all these methods because each method has sort of a different class of problems in which they work well. Diagnostic plots of y versus the components of w hat transpose x may be helpful. For chemometrics, what we used is prediction via inverse regression that I proposed in 2009, and we found that that works really well in our experience. It kind of capitalizes on the nature of chemometrics regressions and gives what seem to be very good answers. So then, 3, iterate selecting q using cross-validation and estimate prediction error based on a holdout sample as usual. So the only change here relative to standard off-the-shelf algorithms is number 2. So the point in the algorithm at which they take the reduced predictors, the components, and generate the prediction, that's where adaptation is required. Otherwise, the algorithms can proceed pretty much as they are. So what I want to do next, let me back up just a minute here, sorry. I mentioned here that what we used is prediction via inverse regression. I'm going to be using that in some examples. I'm not going to talk about the details of that in the formal part of this, but I'm prepared to give you a brief overview should you have questions at the end. So, comparison to methods intended as partial least squares replacements in nonlinear settings. So, the first set of comparisons we have come from the Decatur data, which is a very well-known data in chemometrics, as I understand it. The reason that we use this data set is because in 2014, Shan and others proposed a new method for handling nonlinear PLS type problems. And their method is called PLS slice transform, and it's the one represented in blue, method number 6 in the table. They use the Decatur data for their analysis, and that's why we use the Decatur data, because we wanted to contrast what we could accomplish against their results. So in the data set, there are 172 training samples, 43 testing samples, 100 spectral predictors. Now, lines 1 through 6 in the table come directly from the paper by Shan. We verified parts of the table to make sure we were on the same page, but the results in 1 through 6 come from the paper. Now, the data set has 6 responses, so there are, 3 responses. So there are 3 different regressions involved here. One where y is fat, one where it's protein, and one where it's water. Now, if you look down the root mean squared prediction errors, you see that PLS slice transform does pretty well against all the other methods. Now, all the other methods 1 through 5, are the methods selected by Shan. So this table was presented in their paper. The first 6 lines of this table was presented in their paper to support their new method. So you can see PLS, the standard garden variety PLS with linear predictors, does the worst. That's followed by quadratic PLS and then something called kernel PLS, locally weighted PLS and PLS polynomial, and they do, some of them do better, some of them do worse, but PLS slice transform seems to do well across the range, and certainly does best for fat and for water, and it's about equivalent to the best for protein. Now, PLS slice transform is kind of a clever method. What the authors did is they sliced up the response, and within each slice they assumed linear PLS, and then they glued things back together. Very, very similar to sliced inverse regression by Kirchow-Lee, if you're familiar with that dimension reduction method. So what we did is we took the data, we made sure we were on the same page in terms of methodology, we reproduced the PLS root mean squared prediction errors, for example, and we applied dimension reduction from standard off-the-shelf methodologies plus prediction via inverse regression. And our methods are the last row of the table, and you can see that we really did well across the board. So our mean square prediction error is 1.4 compared to 1.66 for the slice transform method, 0.6 to 0.54, and 1.36 to 1.32. This gave us the kind of encouragement that we were looking for to either push on with this methodology or maybe kind of set it aside and say we need to rethink it. This was really encouraging to see that we could get these kinds of results using the most important part of standard PLS methodology. That's the dimension reduction part. That's really where the thrust of that methodology comes. Using that plus sort of an off-the-shelf prediction method for nonlinear regression. This is a slide just so as a plot of fat versus one of the components, and you can see the nonlinear effect pretty clearly. And this is the kind of thing I mentioned before, that plotting the response versus the components can give you some kind of intuitive feeling for what's happening. You'll notice here that the regression surface, although it's nonlinear, is monotonically increasing, and it's that kind of surface that prediction via inverse regression works really well for. Another data set, Capini in 2020, they developed a neural network for online prediction via spectroscopy of a protein used in the treatment of autoimmune diseases. They really started with a huge data set. They had 35 samples and P equal to some 38,000 spectral predictors. So now P is really, really a lot bigger than N. Their goal was to use neural networks. They reasoned that you can't really do a neural network with that many predictors, 38,000. So the first thing they had to do was get the number of predictors down. And they did that. The first step they did was they systematically eliminated wavelengths until they got down to some 9,000 predictors. Then from those 9,000 predictors, they applied principal component analysis, and they took the first 12 principal component directions. They used those to create new predictors, and they did 12 of them. So they've selected 12. So now we're going from 38,000 to 12. Using those 12 predictors and the response, they then determined the hyperparameters in their neural network via a Box-Behnken design to optimize a desirability function that they developed in their paper. Now, when all was said and done, when they had their methodology set, their root mean squared prediction error over 9 testing samples was 8.6 compared with 15.3 for standard off-the-shelf PLS. So they almost cut it in half, the prediction error. Now, what did we do? Well, one of the things that concerned me was a lot of user injection is needed here. You have to determine how you're going to select the spectral predictors. You have to determine the number of principal components, and there are a lot of other little things that they did to make things kind of work well. We wanted to see what would happen if you didn't do any of that. So we applied partial least squares dimension reduction. That is, we took the W hat from standard off-the-shelf partial least squares. We applied prediction via inverse regression to the original 38,500 predictors. we got a root mean squared prediction error of 8.46. And again, this is the kind of thing that gave us the assurance that we needed to kind of continue on and think there really could be something useful in this methodology. So the main conclusions revisited. The dimension reduction arm of off-the-shelf PLS algorithms, like NIPALS and SIMPLS, and any other algorithm whose weight matrix can be characterized in terms of a Krylov sequence, is serviceable in nonlinear regression. It seems to work really well for the reasons that I outlined. For the best results, the prediction arm may be adapted on a case-by-case basis, but prediction via inverse regression has worked well for us in chemometrics regressions. The prediction via inverse regression, of course, is described in detail in the paper that I cited previously. So Rasmus asked me to stop at about 30 minutes, so I think my time is pretty close to 30 minutes, given the little hiccup we had at the start. So I'll thank you. At this point, I'm done.
Thank you very much, and perfectly on time. So at this point, I would like to ask if there's any questions. And maybe people can just speak up. We don't actually need to use the chat, I think. So I just advise people to speak up.